when scientists cheat and get caught. Last time we said moving forward, we are dropping the demarcation problem and now trying to draw a line within science, an epistemically significant line between good and junk science. To do that, we will look at a bunch of specific cases. The first one will be scientists cheating and getting caught. The idea that scientists could cheat is surprising to some people, especially those people who subscribe to the idea that science is special. Such people falsely idealize science and scientists. In reality, however, scientists are people pretty much like us, not angels. Most scientists, pretty much like everyone else, want money and job security. They also want to make an impact. They want to have influence and recognition for their hard work. And finally, at least some scientists desire power, especially administrative power. The only realistic way a professional scientist can get money and job security is through salary, grants, and tenure. Some scientists can also get money through inventions and patents, but this is largely on its way out. Being a private scientist today is nearly impossible, and most scientific institutions gobble up the intellectual property rights of the scientists working for them. So yes, salary, grants, and tenure are pretty much the only ways. Influence and recognition come from being published in prestigious journals, receiving special titles like named professorships, and awards like the Nobel Prize. If a scientist desires administrative power, on the other hand, they have to climb the bureaucratic ladder. They have to become chairs, deans, provosts, major journal editors, and such. Naturally, scientists desire these rewards. Of course, wherever there is people, there is also diversity. So some scientists might care more about recognition than money, some more about power than fame. But every scientist is motivated by at least some of these rewards. But getting to the rewards isn't easy. In fact, they are distributed by a very stingy group of people. Remember those people who climb the bureaucratic ladder? Those chairs, deans, provosts, journal editors, and such? An individual scientist needs to convince those people to get to the rewards. For instance, to get tenure, a scientist needs to convince her department's personnel committee, her chair, her dean, her provost, and her university president that she is good enough. To do that, she needs to convince journal referees and editors that her work is good enough. To do that, she needs to get grants, which requires her to convince grant committees that she is good enough. So she needs to convince a lot of people with varying degrees of bureaucratic power. We will call the totality of this bureaucratic system the authority structure. You can think of the authority structure as a gatekeeper who decides who gets in and who doesn't. Some scientists think that they are clever. They try to fool the authority structure and skip part of the necessary work to get the rewards. That's what I mean by scientists cheating. Like any attempt to cheat a system of rules and enforcement, sometimes they get away with it. Sometimes, however, they get caught by the agents of the authority structure and they get punished. Today we will look at some recent high-profile examples of scientists cheating and getting caught. David Goodstein, the author of the chapter you read for this lecture, argues that the goal of a scientist who cheats is almost never to insert a falsehood into the body of scientific knowledge. Instead, Goodstein identifies what he calls 3 risk factors to explain their behavior. First, scientists who cheat are almost always motivated by the rewards we mentioned, like money, promotion, and recognition. As you will see, scientists who cheat often describe this motivation as career pressure. What's more, scientists who cheat usually think that they know how the results will turn out if they had gone through the trouble of doing the required work. And finally, they usually work in fields where reproducibility of results is low. After all, if I worked in a field where results are easy to reproduce and I produce false data, it would be extremely risky for me. Any other scientist trying and failing to produce the same data would implicate me for cheating. But if I work in a field where there are a ton of variables that are impossible to control, then I can safely make up pretty much anything I want, and probably no one would suspect me of anything. It is also important to clarify what I mean by cheating. Unsurprisingly, scientific organizations don't like the word cheating. Instead, there is a politically correct and fancy phrase that serves as an umbrella term which they prefer: scientific misconduct. When a scientist is accused of scientific misconduct, this means they committed fabrication or falsification of evidence, plagiarism, error in methodology, or an ethics violation unrelated to the integrity of the data and the results the scientist has reported. Fabricating evidence, or fabrication in short, means making up data. Falsifying evidence, or falsification in short, means changing or omitting data or results. As you might remember, philosopher Karl Popper used the word falsification in a very different meaning. When he said falsification, he meant disproving a theory by experiment or observation. Here and on, we will use falsification to mean changing or omitting data or results. So please beware of these two separate meanings. Then there's plagiarism, which is a failure to credit the original authors or investigators for their work. When I say cheating, I mean one of these three, as they are considered the most serious forms of scientific misconduct. Let's get to examples. Today I will discuss cases of fabrication and falsification. I'll start with Vipin Kumar, a scientist who committed falsification. Kumar falsified his data for a paper he published in the Journal of Experimental Medicine. We will get to the exact nature of the accusation in a minute, but first let's look at Kumar's background, which is pretty impressive. Kumar was a biologist who had a great education and a remarkably successful career up to the point he was accused of misconduct. He studied at prestigious universities in India before coming to the United States for postdoctoral studies. First, he was at Harvard Medical School for 2 years. After that, he came to Caltech. It was there at Caltech Kumar was accused of scientific misconduct. This is an image he submitted with his paper. It's a photograph of the results of DNA analysis. What's remarkable about this photograph is this. Parts of the image appear identical. It's almost as if they were copied and pasted over. And it's kind of obvious. Why is this misconduct, though? On TV, DNA analysis is a magically quick process used by sexy detectives to catch clever serial killers. In reality, it's a messy and time-consuming process called gel electrophoresis. This is the machine used for this process. This tub gets filled with a transparent gel. The gel has holes in one end called wells. The scientist puts the DNA samples in these wells. Then a uniform electric field is applied across the gel in such a way that the end that is farthest away from the wells is positively charged. DNA fragments are negatively charged. Since opposite charges attract each other, the DNA fragments in each sample slowly swim through the gel towards the positive end of the tub. Smaller fragments experience less drag in the gel and swim faster. Larger fragments swim slower and lag behind. The results look like this, a bunch of lines on a photograph. You might be wondering how this helps analyzing the DNA. Here's how. DNA from a person has characteristic fragmentation, which produces a pattern unique to that person. So if two samples of my DNA are put in two wells next to each other, eventually the lines should all line up. But if my DNA is put next to, let's say, O.J. Simpson's DNA, they wouldn't line up because my DNA fragments are of different sizes than his. Of course, that's the ideal world. In the real world, the gel almost always has small air bubbles and impurities. They don't cause any trouble unless there are too many of them. You can even spot these bubbles in this image if you look carefully. Now, going back to Kumar's image, you see several air bubbles. His air bubbles look black because his image is a negative. The problem is Kumar's air bubbles don't look random. Some of them are identical in size and perfectly aligned with each other. The chances of this happening by luck is astronomically low. So ironically, Kumar got busted by his own DNA analysis. When questioned, he said that the lines in his results did not get aligned as well as he had hoped. So he photocopied parts of the image to make the image look more compelling. That means he committed scientific misconduct by falsification. He replaced parts of his data with false data. He defended himself by claiming that he was under immense career pressure and felt as if he had to produce perfect results. He was eventually convicted of the charge of falsification. He was fired from his Caltech position and was put on a 3-year-long ban for NIH grants. However, he had a very prosperous career ever since. He is currently a professor of medicine at UC San Diego. In Kumar's case, we see all three of the risk factors David Goodstein discussed present. First, Kumar wasn't trying to sabotage science. He was just trying to take a shortcut. He just tried to get to the rewards without doing the work for it. Indeed, Kumar thought that he knew how the results would turn out if he did the experiment properly, which is risk factor number 2. He just didn't want to go through the trouble. And finally, Kumar worked as an immunologist, which is a field with remarkably low reproducibility of results. He thought no one would notice that he falsified evidence. After all, if someone tried the same DNA analysis and got very different results, they would have probably shrugged their shoulders and blamed contamination of the samples. And here, Kumar's bet is a rational one. If it were not for the air bubbles, no one would have suspected him of any wrongdoing. The brunt of the consequences on the Kumar investigation fell on another scientist named James Urban, who worked in the same lab. Urban was discovered to have fabricated the evidence for several of his papers. Fabrication, remember, is one of the serious forms of misconduct. It means making up data. It turns out Urban had made up the data for several of his papers. The discovery was made during the investigation for Kumar's misconduct because the whole lab came under suspicion for doing sloppy science. Just like Kumar, Urban also blamed career pressure for his actions. He said that he was lagging behind and he had to fake data to get his manuscripts accepted for publication. He also claimed that he had intended to replace the fake data with real data before the publication of his results. The truth of this last claim is up for debate. On the one hand, one of his papers was published already and he had not produced the data by that point. On the other hand, this might have been the result of the chaos and close scrutiny triggered by the Kumar investigation in their lab. By the time the investigation was completed, Urban was hired by the University of Chicago as an assistant professor of medicine. When the news got out that he had committed fabrication, he was fired. Unlike Kumar, Urban didn't fare well. He faded into obscurity. Urban, too, has all three risk factors. He was just trying to look out for himself. He thought he knew how the data would turn out if he actually did the experiments, and he worked in the same field of immunology with the same low level of reproducibility of results. Poor Urban. He would never have been caught if it were not for Kumar's sloppiness with the air bubbles. Serious scientific misconduct doesn't happen only in biology. It also happens in physics. Perhaps the most remarkable example of this is the rise and fall of Hendrik Schön. Schön worked at the Bell Labs in the field of organic semiconductors, an unusual field of physics with very low reproducibility. Semiconductors is perhaps the most important material for today's technology. They are used in transistors. Transistors are in integrated electronics. Things like consumer computers, mobile phones, GPS, and the internet are simply impossible without semiconductors. Smaller transistors are better for technology. In fact, the sole reason why computers have been getting faster and more compact is scientists' ability to make smaller and smaller transistors. Because if you can make them smaller, you can cram more of them in a given space. For instance, the smallest transistor of 30 years ago is 300 times the size of today's smallest. There is a problem though. We are nearing the limits of what is possible with the available materials, which are inorganic substances like silicon dioxide and germanium. With inorganic materials, transistors can't be made much smaller than 5 nanometers. This is why Schön's field is so enticing, because it promises a new set of materials to make transistors with, which might bring the limits down to or below a single nanometer. And in 2001, Schön claimed to have precisely this, an organic transistor the size of a single molecule. What's more, Schön was incredibly productive. He published one research paper every 8 days for a period of 3 years. That's about 150 papers in 3 years. For comparison, even extremely productive scientists can't produce that many in an entire lifetime. But it wasn't just quantity that was incredible. Most of Schön's work was published in top-ranking journals like Physical Review, Science, and Nature. At the age of 30, he was seen by many as a future winner of the Nobel Prize. Yet, it was all too good to be true. Paul McCarnan, a physics professor at Cornell University, noticed that Schön's graphs looked too neat. If you are like me, you might have imagined that McCarnan did something really high-tech and fancy, like running an advanced computer analysis of Schön's data to catch him. However, he didn't have to do anything fancy. He just photocopied Schön's graphs on transparent sheets and overlapped them by hand. It was that obvious. These are 3 separate graphs taken from 3 separate papers Schön had published. Each graph is supposed to represent the electrical properties of 3 separate substances. These 3 graphs are nearly identical, with the exception of a 5th curve present in graph 1 but missing in graphs 2 and 3. Even the noise characteristics of 2 graphs are identical. Here's another set of 3 graphs from again 3 different papers, supposedly investigating 3 different substances. Once again, everything is the same. Even noise characteristics are the same. The only difference is the scales of the graph axes. Again, 3 graphs, nearly identical data. Indeed, 2 of them are not even nearly identical. They are identical. None of Schön's original data or samples could be found in the course of the investigation. Apparently, he destroyed everything before the investigators could get to them. The investigation report, which I'm linking down below, documents 24 specific allegations like these, and eventually Schön was found guilty in 16 of them. The report indicates, moreover, that this is rather the tip of the iceberg. Eventually, 24 papers have been retracted by the journals in which the papers appeared. What's more, up to 60 papers are questionable because of Schön's critical involvement. Schön also blamed career pressure. At this point, you must have noticed a trend. When they get caught, they all blame career pressure. He was fired from his job and dropped out of professional research completely. What's more, his alma mater in Germany, Konstanz University, revoked his PhD. He also received a lifetime ban from working as a scientist. According to the latest reports, he is now working at an air conditioner factory in Germany. I'm not sure in what capacity, but I close my eyes and imagine a mop bucket. One can only dream. Again, we see all three risk factors present: career pressure, knowing the answer, and working in a field with low reproducibility. The last example we will discuss is Victor Ninov, an experimental particle physicist at Lawrence Berkeley National Laboratory. The equipment of this lab was old and less powerful than their counterparts in Russia, Europe, and Japan. Ninov was convinced by a theoretical physicist that even their inferior equipment could still synthesize new elements. This theoretical physicist predicted that collisions of krypton-68, which is an atom, and lead-208, which is another atom, would produce a new element called element 111. Ninov's team tested this prediction, and in 1999 they reported their discovery of the element 118. The problem was other teams around the world who had more powerful, more capable equipment failed to replicate Ninov's results. Besides, this is a field where reproducibility of results is high, not low. So if Ninov's results were true, they should have been easily reproduced by labs furnished with more powerful accelerators. Suspicion quickly turned on Ninov, who had manually changed apparently the data logs to create the impression that they contained evidence of element 118. To this day, Ninov has denied any wrongdoing and maintained his innocence, but he was found guilty of falsification in the ensuing investigation. Not surprisingly, he was fired from his job at the National Laboratory. He was briefly hired by the University of the Pacific, who later fired him upon discovering his conviction. Ninov retired from physics and currently lives in California. As I said, Ninov denies wrongdoing and refuses to explain why he edited the data logs. But assuming that he is guilty, it's not hard to imagine why he would do it. Discovering a new element is one of the most prestigious achievements a scientist can have. And Ninov definitely thought that he knew how the results would be if the experiment were successful. In fact, he was using a theoretical model as his blueprint. This also explains why Ninov's case is an exception in the sense that he worked in a field with high reproducibility. Indeed, Goodstein speculates that Ninov gambled counting on reproducibility. Ninov knew that his lab's equipment was probably not powerful enough to synthesize a new element. However, other labs, he thought, had enough power to discover it. So he would go, fake the discovery, and when the other labs confirm it, he would be celebrated as the scientist who discovered the new element. Too bad his gamble backfired. Before we adjourn, I would like to say a few things about what Goodstein calls risk factors. I don't think these are risk factors at all, because they cannot predict and explain the behavior of individual scientists. In fact, the first one, career pressure, is almost universal, from the scientist at the humblest community college to the fanciest research lab. Scientists are under constant career pressure. Trying to predict who will cheat or why someone cheated based on this is a bit like saying that having a pulse is a risk factor for murder. Yes, every murderer has a pulse, but that doesn't predict or explain murder. Perhaps the scientists who experience career pressure as emotionally overwhelming are more disposed to cheating. This makes sense intuitively, but it is hard to measure because emotions are subjective feelings. The second factor is questionable as well. Scientists are smart people, and they know that they are smart. Of course, they'll have opinions about how the results will be. This is a function of the combination of high cognitive ability, extensive knowledge, and a dash of hubris maybe. In fact, it would be impossible to explain what Schön and Ninov did without presupposing a healthy dose of hubris. Perhaps factor 2 isn't as common as 1, but it is still common enough to make it meaningless in terms of predicting and explaining misconduct. We are left with the reproducibility being low. This, I think, is the most plausible and useful item. However, there are limits to its explanatory and predictive power. First of all, not every scientist in a field with low reproducibility cheats. What makes cheaters cheat then? That is left unanswered. What is more, perhaps the scientists in fields with high reproducibility cheat just as often, but differently. Remember Ninov, he got caught because the theoretical model he was betting on left him stranded. Maybe this is just his bad luck. Maybe many physicists and chemists out there are falsifying and fabricating evidence as we speak, but they use more robust theoretical models. I myself remember witnessing this many times in college as a physics student in lab classes. Often someone would look at their data and they would knew that it was bad because it didn't conform to the relevant equation. Then they would change or add a few data points and voila, it's all fixed now. If a physics student could do that as a 19-year-old and then get past the TA's review, why would we assume that a veteran researcher with decades of experience can't do it and get away with it? But let's not lose sight of why we are looking at these cases of cheating and factors that might explain and predict them. Our goal, ultimately, is to draw a line between good science and junk science. I don't know about you, but I don't see anything that can draw such a line yet. This brings me to the end of this lecture. Send me an email if you have any questions. Thank you for your patience, and I'll catch you next time.